Hi, my name is Senta Jansen and I'm studying to become a doctor in optics. That's a science about light, and I'm working with lasers. Today though, I would like to talk a little bit about waves, about standing waves in particular, what they are, how they work and why they're important to us. And I'm sure a lot of you have experienced standing waves already. Have you ever sat in the back of the car when the windows were down on one side and you heard the whoop whoop sound in the back? So that's a standing wave forming inside of the car, and you can get rid of it by just opening a window. And we're going to demonstrate this today. So we're now getting up to speed, and the moment we are on the motorway, you should start hearing it. So we can hear it now already a little bit. But with a higher speed, it will become even more audible. If we close the window, you can hear all of a sudden it's all gone. To explain a little bit more and show different examples where we can experience waves, standing waves, apart from in the car, we're going to go back into the lecture theatre now. Another situation where you might have come across waves is when you've seen someone in the gym using those battle ropes. So you can create a wave by flicking this rope up and flicking it down again. I'm transferring energy to the rope by moving the rope up and down to then create a wave. The waves travel away from me at 90 degrees to the rope's motion. These are an example of transverse waves, just like water waves or light waves. Waves transfer energy from one place to another. The waves that I'm making here travel along the rope to the end. But what happens if you get a reflection? This light-up string toy shows a great example of a reflection. A wave is being sent in one direction along the string and is being reflected back on itself. If you have two waves traveling in opposite directions along the same media, you can get what is known as a standing wave, which is a superposition of the two waves. The point in the middle, where the standing wave does not seem to move, is called a node. The areas where you see a maximum displacement from the resting position, these are called antinodes. This is a Reubens tube. It's been developed by two German physicists in 1905 because they wanted to visualize waves. We've got a metal tube and we've got a gas inlet here, which fills the tube with camping gas. This here is the signal generator we're using to introduce a sound wave into the Reubens tube. What you see here is the wave that we introduce. You can see the resting position, it's this line here, that's the undisturbed position. And the amplitude is the point of maximum displacement from the undisturbed position here. You can also see the wavelength. The wavelength is from one point of the wave to the equivalent point on the adjacent wave. For example, you've got the peak to peak, or trough to trough, or you can choose any point on the wave to the equivalent point on the adjacent wave. So this speaker generates a sound wave that travels through the Reubens tube. It gets reflected on the side and travels back. So inside of this tube, there's a standing wave. And because there are holes on the top of the tube, the gas can escape. When we then set fire to the gas, you will see a high point when the pressure inside of the tube is high, and a low point where the pressure inside of the tube is low. And now let's set it on fire. So we've got a standing wave in the tube where there's areas where we've got high pressure and the gas can escape, so you get a high point on the wave. And then the areas around here when you've got a low pressure and the gas can't get out as much, therefore you don't have a flame. When we change the frequency on the signal generator, we see how it's moving and we create a different standing waves where it has now the high points and the low points on a different location. Waves travel at different speeds in different media. For instance, light travels through air differently to other materials such as water or glass. But we can calculate how fast a wave is traveling with the following equation. V equals F times lambda. Let's look how to work this out. So V is the velocity or the speed of the wave. It's measured in meters per second. F is the frequency of the wave, which is how many waves pass a point in 1 second. This is measured in hertz. For instance, if 10 waves pass you in 1 second, then the frequency of the wave is 10 per second, or 10 hertz. And finally, lambda. Lambda is the length of the wave. It's the wavelength as we saw on the oscilloscope. And the wavelength is measured in meters. If you multiply the frequency and the wavelength together, you can find out how fast the wave is traveling. Remembering the wavelength is across 2 peaks of the standing wave due to the reflection. Our frequency in this case is the pitch of the note we are playing through the speakers. Now multiplying them together, we get the speed of the wave. Instead of using a signal generator to create a standing wave inside of the Reubens tube, we can also use an alternative. Dr. Bill Brocklesby.